Let's look at reaction kinetics, and this is a first slide series. So you can define chemical kinetics, reaction rate, and look a little bit behind the reaction rates to what's going on at the molecular level. What's the purpose of studying chemical processes anyway? Why would we study molecular shapes and energies, the effect of pressure and temperature, the thermodynamics of reactions, how much the delta H is or the delta G? Why would we study rates of chemical reactions, and why would we study equilibrium states in a chemical reaction? Well, the purpose of studying all of these things is quite simply control. Chemistry is about controlling chemical processes for the benefit of the human economy. Most specifically, chemical engineering is about that, and our research in chemical kinetics is what we use to control, and therefore to get some engineering control over these reactions to make them less expensive, not just in money and in energy, but also in resources. Science, after all, is at the service of human welfare. So, it is a control to increase the production of useful chemicals like ammonia, which is the basis of a lot of fertilizer and quite a bit in the way of nitrates. Control, we would like to poison any enzymatic process that gets in the way of healing. For instance, we use atropine to reverse the effects of harmful anti-nerve drugs. We can also disable biological systems that have gone haywire. For instance, in seizure disorders, we use carbamazepine, and in certain other circumstances, we use Paxil. These are disabling biological systems that are getting in the way of health. How do we achieve control of chemical reactions? Well, we have to understand their mechanisms, what's happening on the molecular level. How do we understand those mechanisms? By determining what effect a changing condition will have on the rate of the reaction, we can better understand what's happening on the molecular level. Chemical kinetics is the discipline within chemistry that studies the rates at which reactions occur and the factors involved in those reactions. For instance, the rate is proportional to the concentrations of some reactants. The rate is proportional to the temperature of the process. The rate is going to be dependent in some way on the presence or absence of a catalyst and on what that catalyst is. And the rate is going to depend also on the surface area of the reactants that are exposed, and in other ways also dependent on the orientation of the molecules as they strike each other. Well, let's talk a little bit about differing rates of reaction. We know that sugars will ferment into alcohol and carbon dioxide in 1 to 2 weeks completely. Magnesium, however, burns in air in seconds and even faster in oxygen. Iron, however, rusts in a period of years in an oxygen atmosphere. But we can burn iron as well, and you may, at some point, your demonstrator may show you how steel wool, which is a much more finely divided type of iron, burns either in air or oxygen. The same reaction can occur at different rates depending on temperature and concentration. Iron rusting is actually the same as iron burning. Iron is reacting 1 mole with 1/2 mole of oxygen to form a mole of iron 2 oxide. If it's hotter, it goes faster. If we add pure oxygen instead of air, we make the reaction go faster. So, if we heat it up and use pure oxygen, we get an extremely fast reaction. What's the rate of reaction? Well, let's learn from a thought experiment. And in this experiment, reactant A is turning into product B. At time 0, we have all A and no B. we let it run for 10 minutes, we see that a great deal of the A is gone and an equal amount of B has been produced. After 20 minutes, a lot more A is gone, but not quite as much A has disappeared as did in the first 10 minutes. The same thing with B, they're kind of mirror images. After 30 minutes, even more A is converted to B. Now, after some hours, all of the A converts to B at the completion of the reaction. This little line here, you may be aware, means a long passage of time. This is not a continuous line. There's a discontinuity right here. So the reaction rate would be the speed of appearance of products. So let's look at the rates at 2 instants of time, just kind of taking that graph and blowing it up. With a sufficiently small time interval, maybe a millisecond, the graph of concentration versus time is a straight line. And so we can talk about the change in the concentration of A versus the change in time. That's the reaction rate. Change in concentration divided by the change in time. In calculus, you'll use very small increments of concentration of time, and you'll call this dA and the time change dt. If we go to a later time interval, then we can see, again, a very short line, a very short tangent line, perhaps. And we see the same type of calculation after 20 minutes, the change in A over the change in T. And we're not surprised that the new rate is smaller than the first one because we are 10 minutes later. The concentration of reactants is lower, so the reaction rate must be lower. The rate of reaction is constantly changing, reducing as the concentration of reactants reduces with time. The fastest rate is when the concentration of reactants is the highest, right here at the beginning of the reaction. As the concentration of reactants goes down, the rate goes down. It's therefore customary to measure the average rate of reaction by measuring the time it takes for the reaction to proceed to a defined point. Rates are then given as change in mole concentration per unit of time, as in molar per second. We can measure the rate of disappearance of reactants, the rate of appearance of products, or the appearance of a third compound that results from the excess of one reactant when the other is exhausted. Let's take an example, the hydrolysis of butyl chloride. Butyl chloride reacts with water to form butyl alcohol, or butanol, and hydrochloric acid. This acid appears as time goes on, so we should be able to follow the reaction by measuring the acidity of the solution as a function of time, because that will give us how much butyl chloride is remaining by simply subtracting the butyl alcohol from the original butyl chloride. And so we get the concentration of butyl chloride as a function of time here, and about 800 seconds it's nearly all gone. We're down by 80%. The rate at any given time is the negative slope of the concentration time graph, which is the negative slope of the tangent to the curve at that particular time. The reaction tells us that the rate of the reaction is the rate of appearance of butanol, which is the same as the rate of disappearance, the negative rate of disappearance of the butyl chloride. And this is the simplest type of stoichiometric example because we're getting one product for every disappearance of one reactant. Let's take another reaction, the dissociation of hydrogen iodide into hydrogen and iodine elements. Clearly, the rate of the disappearance of the HI is twice as fast as the rate of appearance of either the iodine or the hydrogen gases. So we can write the math differently. The rate is minus 0.5 times the rate of disappearance of hydrogen iodide, and it's equal to the rate of appearance of the hydrogen gas. So it's necessary in all cases to divide by the coefficient on the reactants or the products when trying to define the rate of reaction by the rate of disappearance of products or the rate of the appearance of the products. So this should say disappearance of reactants or rate of appearance of products.